Okay, let's look at actually designing some circuits that have particular frequency responses or transfer functions. And we're going to look at what are known as passive filters today. These are circuits that do not involve active elements like transistors or operational amplifiers. So they just consist of resistors, capacitors, and inductors. Now typically we try to, in our circuits, use capacitors whenever we can in place of inductors. So for these, some of these circuits we're going to look at, like a first order low pass or high pass, you can build them using either a resistor and an inductor or a resistor and a capacitor. The resistor and capacitor circuits are preferred because practical capacitors act more like ideal capacitors than practical inductors act like ideal inductors. And it's also true that at least at audio frequencies, at lower frequencies, inductors tend to be quite heavy and large, so they take up a lot of space. And if you're interested in and expensive as well compared to capacitors, so kind of three strikes against them when you're trying to employ these filters at lower frequencies. Now at higher frequencies, you can get appreciative inductive impedance at higher frequencies with small inductances. And so there at radio frequencies, inductors become a little more practical to use than they do at lower frequencies. So the first circuit we're going to look at is what's called a first order. And first order means it has this 20 dB per decade roll-off response. So first order low pass, and what that would look like, the frequency response is this 1 over 1 plus j omega over omega c. And this is kind of your go-to low pass filter, and we can build it just out of an R and C resistor and a capacitor. And so if you find yourself in need of a low pass filter, this might be your first attempt. And then if it doesn't provide a sharp enough response, then you can look at maybe a higher order low pass filter. But if you go through the analysis of this, and we've done this before, you'll see it has this transfer function where omega c is 1 over RC. And the Bodie response for this thing looks like this. We're plotting this. So our pole frequency is at omega c, which we can set by setting the product of R and C. So kind of one of these is arbitrary. Typically you might pick a value of capacitance using a convenient value that you have on hand, and then calculate the resistance that you need in order to get the cutoff or corner frequency that you need. So again, for frequencies omega less than omega c, the response is equal to 0 dB. So this would be H in dB. And then we've got a 20 dB per decade roll off above minus 20 dB per decade roll off above that corner frequency. And so this is what a low pass response looks like, again, on this dB scale on semi-log graph paper. The corresponding linear response would start at 1, which is 0 dB, and then look more like this. This is the magnitude of H as a function of omega, and it never reaches 0. And then the 3 dB omega c is actually where our response is then down to 0.707. But this exponential, or not exponential, but rather this 1 over omega roll off here on semi-log paper, and the Bodie plot becomes this straight line minus 20 dB per decade roll off. So again, this is a first order low pass. We can actually get a first order high pass. I will just mention back at this first order low pass, again, you can kind of reason your way through it being a low pass filter. At low frequencies, the capacitor is an open circuit, and so there would be no current and no voltage drop across the resistor, and the output voltage is equal to the input voltage. At high frequencies, our capacitive impedance is very small. It's 1 over j omega c, remember? So as omega becomes large, our capacitive impedance drops to 0. And in this case, this would be a short circuit. There would be current flowing. There would be voltage across R. In fact, all the input voltage would be across R, but the output voltage would be nearly 0. So that's, again, characteristic of a low-pass filter. If we actually, you could use an inductor in place of the resistor, use the resistor in place of the capacitor, and you could have an RL low-pass circuit. But again, the RC circuits are typically preferred. We can get a high-pass filter by actually just swapping the capacitor and the resistor. We can get a first-order high-pass. So R and C, VI phasor, VO phasor. And if you go through the circuit analysis of this, and I encourage you to do that, you can work the response into this form. J omega over omega C, 1 plus J omega over omega C. Where again, omega C actually has exactly the same values as it does in its low pass counterpart. The magnitude response for this now in the Bode plot, remember it has a simple 0 here. So when omega is equal to omega c for frequencies below that, it's going to roll off at this minus 20 dB per decade rate and go through 0 dB when omega is equal to omega c, when this term is 1, because 20 log of 1 would be 0 dB. So this is actually, because we're going to the right, this is a 20 dB per decade increase. Okay, and then we have this pole term. You know, this would continue to increase, but we have this pole term that kicks in at omega equal to omega c, and then so our response would look like that. Okay, and this is characteristic. This is a high pass response. Again, on a linear scale, what you'd see is this thing looking something like this. You know, where it approaches 1 at high frequencies. This is H dB. This is the linear scale, and then approaches 0 as we approach omega equals 0. Okay, and so then first order, a high pass, you tend not to use high pass filters as often as you encounter low pass filters, but they are occasionally useful. Okay, so I'll come back and want to talk about one other very useful circuit. It's actually a bandpass circuit.